Hello, and welcome to the Academy of Useless Ideas. Let's take a moment to remember what makes the real numbers so special. They are not just your average run-of-the-mill numbers. They are an extension of the rational numbers that have the magical power of the least upper bound property. What's that, you ask? Well, it's a fancy way of saying that every non-empty upper bounded set has a supremum, which is like a wannabe maximum, if you will. Let's talk about the set of numbers whose square is smaller than 2. This set is bounded, but it doesn't have a maximum. It's like a party with no clear winner. But never fear, because the supremum is here to save the day. The supremum is the next best thing to a maximum, like the runner-up in a race. For this particular set, the supremum is the square root of 2. It's not technically part of the set, but it's the best we've got. Think of it as the ultimate outcast. Better than everyone in the set. So good that it doesn't even belong. When we extend a number system, we risk losing some of the good properties of the previous system. For instance, while the integers have the least upper bound property, this property is lost when we extend them to the rationals. It's possible that our construction of the rational numbers destroyed some of their nice properties. Specifically, we want to make sure that adding the irrational numbers didn't introduce any infinitesimal elements. Let x and y be positive elements in an ordered field. We say that x is an infinitesimal with respect to y, or equivalently that y is an infinite with respect to x, if for every natural number n times x is smaller than y. An ordered field that contains no infinitesimals is said to have the Archimedean property, a fancy way of saying that there are no tiny elements in the system. Let's take the natural numbers as an example. Even though they are not a field, the definition of infinitesimals still makes sense because the operations of addition and multiplication are defined. Suppose that we have two positive natural numbers a and b. Let's assume for the sake of a contradiction that a is infinitesimal with respect to b. This means that the set of natural numbers of the form n times a is upper bounded by b. However, since we are working with the natural numbers, this set should have a maximum. This leads us to the conclusion that there exists an n such that n times a is smaller than b, but n plus 1 times a is not smaller than b. But this contradicts the fact that a was an infinitesimal with respect to b. We have not proven that every bounded set of the natural numbers has a maximum, but for those who are curious, this follows from the well-ordering principle, which itself follows from the principle of induction. The Archimedean property holds for the rational numbers as well. To see why, note that any two rational numbers p and q can be written with a common denominator. By multiplying both p and q by this common denominator, we obtain two natural numbers. Then we can use the fact that the natural numbers have the Archimedean property to show that the rational numbers do as well. Let's investigate whether the real numbers are Archimedean or not. We don't want any sneaky infinitesimal pairs slipping in and notice it. We can't rely on the existence of maximums this time. We need the least upper bound property instead. You remember that supremums are like the cool older siblings of maximums, right? Good. So let's assume for a moment that x and y are positive real numbers and x is an infinitesimal with respect to y. That means that the set of numbers of the form n times x is bounded above by y, and hence has a wannabe maximum, a supremum, which we'll call alpha. Now, if alpha were an actual maximum, we could use the same trick we did with the natural numbers. But alas, supremums are just posers, and we need to get creative. Luckily, we can still wrangle out our way of this conundrum. We can find an element in the set that's larger than any value smaller than the supremum. Since x is positive, alpha minus x is smaller than alpha, and therefore we can find an element of the form m times x that is larger than alpha minus x. Since alpha minus x is smaller than m times x, we conclude that alpha is smaller than m plus 1 times x, which contradicts the fact that alpha is an upper bound. Did you know that the rational numbers are sneaky little creatures hiding in plain sight? They're so tight that they manage to fill all the gaps between different real numbers, making them dents in the reals. To prove this fun fact, let's take two different real numbers, x and y, with x being the smaller one. By the Archimedean property, we know that there is an integer n such that n times y minus x is greater than 1. That means that we can catch a sneaky little integer m hiding between nx and ny. And by dividing m by n, we can expose the rational number hiding in plain sight between x and y. The idea is simple. We stretch the difference between y and x until we can see an integer between them, and then we shrink it back down. But don't be fooled, we still need to prove the existence of m, which can be a bit of a technicality.